Hello, everyone. My name is Gerard Gatch, and I'll be the moderator for today's webinar on the topic of UV-based dynamic process control of twin column LPLC system, otherwise known as AutomAb. This is one in a series of more than 10 webinars on multi-column chromatography for applications in the production of protein therapies. We understand you have limited time and came here to hear the content, so we'll forego formal introductions of our company until the end of the webinar. Just a few housekeeping notes and we'll commence with the presentation. Today's seminar is approximately 20 to 25 minutes long, leaving plenty of time to answer any questions you may have. This presentation is focused on a unique feature of twin column chromatography applied to the capture step in the purification of biomolecules. This webinar will only briefly describe continuous capture chromatography principles before focusing on the proprietary control scheme. We highly recommend viewing the webinar titled CaptureSMB, How Does It Work? That webinar goes into detail on the basic methods employed in multi-column chromatography in the capture step. We invite you to explore our other webinars that cover topics such as these and more attributes of this system. These are 10 to 20 minute presentations by subject matter experts. Today's presentation will cover these topics. Talk about the twin column system and give you just a brief overview. We'll go into AutomAb technology and how does it work, present a case study, summarize, and then take questions. Today's presenter is Thomas Müller-Spath, who holds the position of Chief Technology Officer at YMC Chromacon, based in Zurich, Switzerland. Thomas is inventor of more than 10 patents and has authored and co-authored more than 30 scientific articles and book chapters on continuous chromatography for biopharmaceuticals. Thomas frequently presents at international conferences as speaker and also co-chairs workshops on continuous chromatography. We are pleased to have him. Please welcome Thomas.
Hello, everyone. Welcome to my presentation about the UV-based dynamic process control of twin column LPLC, which is also called AutomAb. Thanks, Gerard, for the kind introduction. So let's jump right into the topic. Why are we using continuous chromatography for capture? And then the next question will be, why do we need the UV-based control? So first of all, why do we need continuous chromatography for capture? So let's assume we have a protein A capture step. Here the resin capacity utilization is typically only 40 to 60%. And that is because when we load the column with a certain flow rate, the column fills up only slowly with monoclonal antibody, and which is shown here as yellow shape in the schematic. And the column actually has a large unused resin capacity because we have a diffuse breakthrough front that is forming as the column is loaded. This front becomes even more diffuse the higher the linear flow rate is that is used in the column. So if we want to increase productivity, the capacity utilization becomes worse. When antibody is starting to break through at the end of the column here, at the column outlet, we have to stop the loading in order to avoid a yield loss, right? So that leaves us with the unused resin capacity. Also, the breakthrough front shape is due to is a function of particle size and concentration, but with typical resins used in protein A capture, we have 40 to 60% utilization. Protein A resin costs in industry are around $10,000 to $15,000 US a liter, and size of protein A columns in manufacturing can be 100 to 250 liters. So this means, assuming the lower resin price, that one packing is worth $1 million to $2.5 million US. So it's quite some resin capacity and that is wasted here, which is associated with huge resin costs that are wasted. Okay, now the idea of continuous capture is to improve the capacity utilization by splitting this one column here into two smaller columns, or columns with shorter bed height, to fully utilize the capacity of the first column before it gets cleaned and re-equilibrated. So like this, the column will only be eluted when its capacity has been fully utilized. And this saves resin capacity utilization and resin costs, and production column savings can be more than 5 or 0.5 million US dollars per packing. So again, Gerard mentioned this has been touched on in a separate webinar on CaptureSMB, how it works. So and I would like to refer you to that webinar if you would like to learn more about the resin cost savings and other associated savings like buffer savings. And again, just very briefly in an animation, how does CaptureSMB work? We have our two columns here. We load the two columns in series. We overload the first column on purpose. Sorry for that. And the breakthrough of the first column is loaded onto the second column that's interconnected. Now, when that first column has been fully loaded, we take it to the side. We wash it and we elute it to recover the product, and then we re-equilibrate it, and then we put it behind the first column with the second column, which then becomes the first column and has been partially loaded. So we continue then to load this first column here, and again the breakthrough is captured in the second column. This is a cyclic process here. In this schematic, one cycle is shown, and also startup and shutdown are shown, so we can get into this process by means of a startup step that takes into account that the columns are empty initially, and then we can go on in this cyclic process until all the starting material has been consumed, or until basically or as long as in case of perfusion fermentation, in case of continuous upstream, and as long as our continuous bioreactor is operating. Okay, so this process is useful for both fed batch and continuous upstream. Okay, now the dynamic process control, and this sort of implied with continuous upstream. Sorry, to go back here. Related to continuous upstream, it means we can have titer variations of the starting material going into this process that we want to account for. Also, when the process goes on for a couple of cycles, what we may actually see here is resin degradation over over the number of cycles, so which usually takes place due to the cleaning in place of the columns when they are in the disconnected mode, which uses usually caustic soda. Okay, so now our dynamic process control concept that we're using for this CaptureSMB process, it addresses the column capacity decline, which is important in both fed batch and perfusion processes. It addresses feed titer variations, which happen in perfusion processes, and it can also address buffer variations. And what it uses is the information obtained from the UV detectors of the process. So we have one UV detector located behind each column, called UV1 and UV2, and these UV detectors will record a UV profile as the antibody and the impurities are breaking through from the first column into the second column. So again, with CaptureSMB, each column has its own detector. So the AutomAb monitors the UV signal of the flow from the first column and keeps now the antibody load onto the second column constant by adjusting the interconnected loading time. And the adjustments that it makes are only made within the normal operating range of the interconnected loading time. So as you've seen from the process schematic, there are states where or phases where the CaptureSMB process has an interconnected loading. This is shown here, and during that interconnected loading, we will first see in this UV detector here a UV signal rising, and then next an antibody signal rising above that plateau of the impurities that you can see here. So again, how does this look like in the CaptureSMB process? So in the CaptureSMB process, as explained initially, we have a cyclic process that can go on for a pretty long period of time, or essentially forever until all the starting material is used, or as long as the perfusion reactor is running. So here we get these repetitive patterns in the UV signal. This is what you see here in the upper left corner are the two UV signals from the two columns. We have product dilutions, these are the high peaks, but we also have the breakthrough from one column to the other of monoclonal antibody. So this on the lower right here shows you one cycle of the process with the two product dilutions here. And you can also see the impurity baseline here from the two columns. And the breakthrough of antibody from one column to the other column. So what is important here to see now, if we take this phase, for example, we see here that the UV2, or column 2 is upstream of column 1 here. So here column 1 is upstream of column 2. Here column 2 is upstream of column 1. So they change positions, which is obtained or reached by valve switching. So UV2 now sees first an impurity baseline, and then it sees antibody breaking through. So this antibody breaking through here, detected by UV2, is captured on this red column here. Now, this column here, this does only see impurities breaking through. It does not see antibody breaking through at its outlet, which means that all the antibody that has been eluted from the blue column here is captured completely in the red column. And at the outlet of the red column, we only see the impurities that are flowing through, which are UV active, such as certain host cell proteins or media components. And so this shows exactly what we want to achieve: breakthrough from the first column and no breakthrough at the same time during the interconnected state from the other column. Okay, so now we can overlay these 5 cycles that we've seen in the previous slide to check if we have really reached a steady state. Steady state means that we have constant product concentration and quality, right? So, and if we keep the loading time and flow rates and everything constant, then we can reach a steady state, but only if feed titer and quality remain the same, if column quality remains the same, if the buffers are the same, if the flow rates are the same. So if everything stays constant, we can get and maintain a steady state. However, in real life, we have feed titer variations, we have column quality changes, so column degradation. So in that case, in order to keep the process under control and to keep the steady state, we can use, or we should use, a UV-based process control. The alternative is we add safety margins, which then come at the cost of productivity. So by underloading the columns, of course, we can also account for a certain column degradation, which will be obtained a couple of cycles ahead, right? But it's not optimal in terms of productivity. Okay, again, so how does the AutomAb, the UV-based dynamic process control, work? So again, let's put ourselves in the position of the first UV detector. We see impurities breaking through at some point as the load is injected here or loaded into the first column. At some point, we will see the antibody breaking through from this column here. And once we have completed the loading to a certain degree, we stop the loading and we wash this column here to move any unbound material, which is still in between the resin particles, into the second column. And then we elute this fully loaded column here. Okay, so now the UV-based control is working based on integration of the breakthrough area of the monoclonal antibody, which is directly proportional to the antibody mass that is leaving that very column. So this chart here, or this chromatogram here, shows you the two integrated areas from the first, or from the blue column and the red column, and also shows you where the baselines are taken. So the baselines for the integration are taken from the impurity signal in the same cycle when the column is in the downstream position. So antibody is breaking through, the column is in the upstream position, it's upstream of the other column, and actually when it's in the downstream position, we only expect impurities to break through, and that's when the baseline for the integration of this area is taken here. So this means that every detector takes its own baseline. So this means that it doesn't matter if the detectors are accurately calibrated against each other. So as you see in the case here, the baselines are different, and the detectors are not calibrated against each other. Nevertheless, just by taking its own baseline, every detector, or the signal of every detector, will be correctly integrated. Okay, so the controller now, it watches the UV signal and it integrates the UV area under the curve of the antibody signal, which we call preload-area. Then it checks if the preload area is larger than the desired preload. If it's not larger, then it just continues to load the field. And if it is larger than a certain threshold value, so if the area has exceeded a certain value, it stops the loading and continues with the process. So what we then see, and just schematically, with the high titer, the preload area will be reached earlier than with the low titer. However, the preload area in both cases will be the same. In the second case, with the lower titer, we just have a slower increase, but eventually the area will be the same, and then we stop the loading. This leads to the same elution peak concentration in both cases. So we wanted to show this experimentally, and we did a CaptureSMB run with a titer of 6 gram per liter in the harvest. And you can see here now this run was operated, and the run duration was less than 660 minutes, which is marked here by this purple dashed line. We got a certain product concentration of around 32.5 to 33 grams per liter. Now we diluted the harvest material and ran the process again with the same operating conditions, just with the AutomAb activated. So the harvest was diluted 20%, which means it was brought down to 5 gram per liter. And you can see here now the run duration is larger than 660 minutes. So the signals, which were here now stopping as the run was completed before 660 minutes, now extend beyond the dashed line, beyond 660 minutes. And this shows you that the controller has actually prolonged the interconnected loading time to account for the lower titer. So the same situation as we've seen here, longer loading time with lower titer, has been experimentally verified here. And as a consequence, the product concentration was staying the same. So 32.5 to 33 grams per liter, also with a lower titer. Without the AutomAb, with a 20% lower titer, we would have expected a 20% lower product concentration, so with fixed loading times. So that shows how the controller has worked nicely for this case of reduced titer. And we got a constant yield also of 96 to 97%. Now, what happens if column capacity changes due to resin degradation? So let's say here we have two columns. They both have the same column quality. We get similar elution peak heights. We get the same preload. Now, if one of the columns decreases in capacity. It means that we see an earlier breakthrough from that column, which means the resin capacity is lower. We reached breakthrough earlier, that essentially the capacity, dynamic capacity, but also static capacity is decreasing. This leads to a smaller elution peak of the second column. Essentially, you're loading less, so your elution peak gets smaller. Okay, also this we verified experimentally. So we did a CaptureSMB run. We started with a first column set. We achieved a loading of 49 grams per liter. And then we, at some point after 7 cycles, we inserted a column with a lower capacity. So one column had a 10% lower capacity. And the AutomAb now became effective and reduced the load by looking at the preload area, by the way it works, right? So preload area was reached earlier. The interconnected loading time was stopped earlier. So it reduced automatically the load to save the yield. And as we can see, the yield was almost the same. So we have reduced the load here by from 49 to 46, but we almost kept the same yield. So despite capacity change, the yield was preserved, and titer variation is important. It's not only important in perfusion culture, but also when you actually have different harvest batches in fed batch fermentation, and you don't have, let's say, an accurate measurement of the feed concentration by the time you want to start the CaptureSMB run. One advantage also of the AutomAb UV-based control is that in conjunction with a two-column process, it can use the interconnected loading time as freely adjustable control parameter. So whenever 2 columns loaded in series are finished, you can stop this loading and continue with the process. Now with a multi-column process that uses more columns, like 3 or more, we call this 3+ column processes, there's something going on in parallel. For example, recovery and regeneration steps, washing steps. So in that case, the adjustment of interconnected loading is not straightforward because something is going on in parallel. So we've illustrated it with this small cartoon here. So in case the UV-based control in a 3-column process says, hey, we've reached our UV threshold, we've reached our preload area, stop the loading now and continue with the process, then this column will say, recovery and regeneration, I'm busy, sorry guys, I'm busy, you have to wait for me. So then reduced waiting times will be introduced, and this will reduce productivity in a 3+ column process. So again, the advantage of the 2-column process when it comes to the operation of AutomAb is that interconnected loading time is available as freely adjustable control parameter. The AutomAb is also scalable from the Conticrom benchtop twin column scale to the twin 100 and twin 1000 scale. And I think with this I will conclude the presentation and let Gerard talk a little bit more about the systems. But again, summarizing this presentation, the AutomAb is very beneficial together with twin column chromatography as it handles variation of feed titer and adjusts for resin degradation. It operates automatically, so you can set it and let it run. And it's very accurate also. It doesn't require detector calibration of one detector against each other or of one detector against a detector measuring feed concentration. It's available at bench or also, of course, on production scale. So with this, I'd like to thank you for listening and hand it over to Gerard for some final remarks before we move on to the Q&A session.
Thank you, Thomas. Again, a really insightful presentation by YMC Corporation. You may know YMC as a leader in chromatography, producing bench and prep scale, HPLC and LPLC systems, packing resin, analytical columns, and DAC columns since 1980. YMC is a global company with manufacturing and offices in over 10 countries. However, what you may not know is that YMC recently purchased both Chromacon and the former Liwa Process Technologies, adding significantly to their 40-year history to now lead the industry in the emerging area of multi-column or continuous chromatography. The result of these applications is a seamless platform from bench to production scale for continuous chromatography. Just a reminder that other aspects of this topic are covered in focused webinars. And now I would like to bring it back to Thomas for the Q&A. And Thomas, we do have a couple of good questions lined up, but the audience, we have room for a few more also. We'll keep it short. First of all, Thomas, how is the controller validated?
Yeah, so the controller essentially operates within an operating space, within a design space that has been defined in previous range finding studies. So we do not let the controller basically operate outside a defined window of interconnected loading times.
Okay, the next question is, do I have to use the UV-based control? I guess this person's asking, is it essential to use AutomAb, or can you do without?
Yeah, again, so I touched on this. So it's possible also to operate with fixed time intervals, so with fixed interconnected times, but then you would have to account for resin degradation that occurs sometime over the cycles in the future. So you may need to, depending on how fast your resin degrades and how long you want to operate, load up to 20% less, I would say roughly. So reduce your interconnected loading time by, yeah, somewhere in the range of 10 to 20%. And also that would reduce your productivity by the same factor to account for resin degradation. So yeah, it's possible to operate without AutomAb, yet it comes at the cost of productivity.
Very good. A few more questions have come in. How does the controller account for baseline drift?
Yeah, so the controller, as shown, takes its baseline from in the same cycle of the same UV detector. So whenever the baseline drifts of that UV detector and the impurity signal changes in magnitude, it will be accounted for by the AutomAb. So that baseline will be then used for the next integration. So, and we think that within the same, if we do it within the same cycle, the change in the calibration of the UV detector is usually not that dramatic.
Good. Next question, what is the difference between AutomAb and delta UV control? I'm assuming that's another control mechanism.
Yeah, that's another control that's based on measurement of UV. So that delta UV control uses the UV signal, the actual absolute signal, whereas we are using with the AutomAb an integrated signal. So the AutomAb relies on the detector, so one detector that's measuring its own baseline. So each detector is measuring its own baseline, and then it calculates or integrates the area based on that baseline. So in the delta UV control, the UV signal of one detector is compared against the feed signal, and then the percent breakthrough that is reached in the column that is loaded is calculated as ratio of the breakthrough signal and the signal determined by the detector in the feed line. So the difference is now you have in AutomAb you have one detector located behind each column. In delta UV you have one detector located behind each column, and then you have one detector in the feed line that the signal is compared against.
I guess along the same vein, is the UV device proprietary or commonly found cell?
Sorry, can you repeat that question?
Yeah, is the UV device, I'm assuming this, the questioner is asking, is the UV device that's employed in the AutomAb, is it a proprietary device or is it just a common UV?
Okay. Yeah, it's a common UV detector. So it's important that, however, the detector is not oversaturated. So when it measures the antibody signal, right? So a small path length is recommended in the flow cell here, and a higher wavelength, so potentially 280, 290, or 300 nanometer. So this, we have to make sure that we can actually see the signal of the antibody that's breaking through. So again, short light path length, like 0.5 millimeter, and yeah, a higher wavelength, somewhere between 280 and 300 nanometer. But there are many detectors which fulfill these specifications.
Okay, we have one question, but it's broken into two different parts here, if I'm reading this correctly, and then we'll wrap up. Can this be used on batch capture? And then the following question is, will this control be a benefit for multi-column polishing schemes?
Yeah, so in principle, the control can be also used for batch capture. But in batch capture, we do not want to have breakthrough, right? So at the onset, in principle, we could use it at the onset of the breakthrough, but at that stage we are already losing some antibody. So yeah, it's not ideal to use it there, because essentially it would kick in when it's already too late and we're already losing antibody. Second question was if it can be also used for polishing. So in case of polishing, we usually do not overload the first column. So to the extent that we capture breakthrough on a second column. So in polishing, typically we do not fully exploit the capacity of the first column. So I'm talking about bind dilute polishing now. There's also polishing that is done in flow-through mode, where the product is breaking through and the impurities are bound. And here, usually the impurities are present in such low quantities or such low concentration that it will be difficult to see the breakthrough of these impurities in the UV signal. Right? So we're talking here about usually trace compounds which are present maybe in 1, 2, 3%. So they're not the major compound like the antibody is in the case of capture from cell culture harvest. So I would say very limited applicability in batch capture and polishing of this of AutomAb.
Okay, very clear. We're nearing the end of our time. I want to thank the audience for your participation and your questions. Questions or applications, you can reach out to us at info@ymcpt.com. That's info@ymcpt.com. Again, in a day or two, you'll receive a link to an archived version of this presentation and a link to associated reference documents where you can learn more about AutomAb. Please share these with your colleagues if you think that they'll be of interest to them. And a reminder that this is one in a series of about 10 webinars. So we'll end our session now. Thank you and have a good day.
Thank you. Have a good day. Bye-bye.